Hi, welcome to our webinar covering advances in flood consequence assessments. I'm your host, Krey Price. I am coming to you from Perth, Western Australia, and excited to be hosting this webinar today with some of the experts who wrote the book on the subject and the software as well. So today we'll be joined by Paul Risher, Woody Fields, and Mark Forrest. So this is a very timely topic. Around the world, we've got all sorts of weather events going on. Just had some evacuations last week for some cyclones and tropical storms coming up. But look at this, we're spread around all around the planet. It's pretty evenly distributed today. So thank you for your attendance, especially those who are tuning in at odd times of the day. We're just delighted to have our speakers on board. Paul Risher, who's a senior water resources engineer with HDR, has been using this software for a long time. He'll tell you a bit more about his career. Paul, if Paul's there saying hi, and Woody Fields as well. Woody's got a substantial role with the Corps of Engineers with the software that we'll be showing you today as an example of one way in which we can run these flood consequence assessments simulations. Great. And for those of you who have never used flood consequence assessment software before, there's a dividing line here. We're going to cover some details. This is called agent-based software. So pardon my background here. I don't think I fit into this mix, but agent-based, actually I should be using this one. Agent-based software means that you're tracking the individual throughout, and that probably wouldn't have been possible just a few years ago. Now we can watch what happens as individuals try to get onto different freeway routes and where the water is coming from in all directions. It used to be you were limited in the directions that water could flow in. Now we can have it moving in any direction at all, and the people can be fleeing the scene in any direction at all. I don't mean to make too much light of it because this is a serious topic. I should actually be using the one in the rain here, since this is what we're running away from, is the water. But this does, this does involve loss of life software. So, all jests aside, this is serious business. This is something that can help the world, and this is why we put this out there. The more we know about where people go, the better off we are. We can save lives doing this. So that's what it's all about. We'd like to educate the industry on this. I want to get educated myself on this better so that I understand what goes into this a little better, and we can cover some of those things on this presentation. So with that, I'm going to turn directly over to Paul, and then when Paul's done, we will cover a couple of things about specific to Australia, because this is the Australian Water School when he's done, and then we'll open it up to the Q&A. All along the way, Woody will be able to answer your questions on the chat line. Mark Forrest is on board as well to answer any technical questions about hydraulic modeling software and things like that. So thanks, Paul, over to you.
Thanks, Krey. Really appreciate having me here. And also appreciate the support from my colleagues, Woody and Mark, to back me up with any questions. They both have more experience in aspects of these topics than I do, so it's great to have them here. A little bit about myself. I work now for HDR Engineering, but spent 9 years with the Army Corps of Engineers, where I assisted with some of the development of HEC-LifeSim, which is a flood consequence model. I'll be sharing from that perspective as I talk to you here, but speaking generally in terms of flood consequence models. A couple of topics we'd like to discuss today. First, I'll start with a little review of some of the flood risk terms, and then describe kind of the purpose of consequence modeling. Why do we want to undertake it? Then we'll give you some things to consider when selecting a consequence model for your risk assessment. Then we'll talk about defining the key principles to any consequence model, and outline some of the major components that go into the model, and we'll discuss a little bit of the data sources where you can find those. And lastly, I'll demonstrate some of the results and output from HEC-LifeSim especially, which is typical of other agent-based software as well. First, a few definitions. Risk, as I'm sure most of you are aware, mathematically is the probability of some bad event, in this case a flood, and multiplied by the consequence of that occurrence. And the consequence, how we quantify that, is different for different types of consequence. We're going to focus today on life safety consequences, but you could also have economic damages, environmental impacts, cultural impacts, or even agency specific. If whoever is conducting the study may have damage to the reputation if a dam fails, or loss of public trust, that type of thing. With regards to life loss, a couple of terms we need to keep in mind are, first, the population at risk, and that's the starting position of everybody who is in the floodplain is the population at risk. They could be impacted by the flood. A subset of that population then is exposed or threatened. So after a warning goes out, people take protective action and evacuate. There's some people left behind who are actually interacting with the flood, and those are the exposed and threatened population. It's kind of interchangeable term. Another thing that we need to know about is the fatality rate, which is applied either to that exposed population or to the population at risk, depending on the type of model that you're using. So it's a point you need to be aware of, that the fatality rates are a little different depending on which model you're using. And the last thing to be aware of is direct versus indirect fatalities. The consequence models that we're using are only estimating direct fatalities, which is people who come in direct contact with the water and experience the physical forces of that water. So they're drowning fatalities, or in a structure that collapses, or a vehicle that's washed off the road. But could be a whole host of indirect fatalities that are a consequence of the flooding, but not directly caused by it. So, for example, if you're evacuating and get into a car accident, or if you have a pre-existing medical condition like a weak heart or something, and the stress of evacuation causes a heart attack, or you can't get to medical treatment for some type of minor injury, then those are the indirect fatalities. And so we're not calculating those, but they're an important consideration. Here's a more conceptual model of risk, when risk is the probability and severity of an adverse consequence. There's these components of the flood risk framework. This is kind of built off an example from the Corps of Engineers again. So the first thing you need to think about is, what is causing the harm? How do we characterize that, in this case, the flood hazard? So typically we have a model to estimate what that hazard looks like. Then we want to know how the system is going to react, the performance of man-made and natural systems. So the river system, for example, or levees and dams, coastal dikes, that type of thing. Then it's important to know who and what can be harmed. So we need to account for structures and people that are in harm's way. And then, how susceptible are those people to harm? So if they're exposed, does that result in a fatality, or maybe not? Their vulnerability is important. And last, how much harm for us to quantify? Going back several years, this is one of the key documents that led to understanding of consequences and risk. It shows the annual probability of failure of several different man-made and natural disasters, and kind of the range of life loss that they're accustomed to. And this one was developed to talk about dams, which you see there in kind of the middle to lower right around 10 to the -4 annual probability of failure, and 10 to a few hundred life loss. That concept from this figure was really turned into a tolerable risk guideline, which you see here an example of a risk matrix developed by the Corps of Engineers in the United States. And it's been adopted in similar fashion by many other dam and levee safety agencies. And that 10 fatalities in 10,000 is one fatality in 1,000, and that represents the red diagonal line there. So that's how that came to be. There's also a range of the levels of risk analyses that we need to be aware of. You may have a portfolio screening, which is a real, quick and dirty kind of estimate of the risk. Example here in the lower left of a levee screening for the Corps. The next level of that is a semi-quantitative risk assessment, which goes into significantly more detail and try to understand the probability of failure of a structure in particular. And lastly, you have a fully quantitative or a detailed risk analysis. And on the right there, you see the boxes with a best estimate represented by the dot in the center of that box. And the uncertainty in that risk is quantified both in terms of the probability of failure and in the number of fatalities. So in order to understand the risk, we need to be able to quantify the number of fatalities, and the consequences model is the way we do that. For risk assessments, it's important that the consequence model is scalable, meaning it needs to adapt to the level of risk assessment you're conducting. It should be flexible so that you can look at different types of events, from dam failure to riverine to coastal flooding. And it needs to be defensible so that you can understand the reasoning behind the estimates. So, where did this estimate come from? And having a piece of software where you can have control of the inputs and document them really helps with providing a defensible result. The process that's typical for consequence assessment is a four-step process. The first being a flood analysis, and it's important to understand the full range of hydrologic loading and to decide on the flood scenarios that are going to be used to model the consequences. So two examples here from dam safety world. The upper one is a gate failure, which has a much smaller floodplain than an overtopping event of the entire dam, which would result in failure of the whole dam. So that's much different hydraulics that would be input to the consequence model. And so it's important that those are developed in tandem, because what comes out of that flood analysis is arrival times and depths and velocities that are used in the consequence model. The second piece then is the direct consequence analysis, which is the subject of our conversation today. And after that is additional consequences that may need to be estimated. Like I mentioned before, indirect life loss. You may also want to look at lost benefits from a damaged structure or repair cost. And the final thing is really to build the case around all of this, to add discussion and context to the flood analysis and the consequences and how those came to be. So this is best practice, just kind of showing the inputs to consequences. You need to have a good understanding of your hydrology as it applies to rain and fall runoff events or reservoir operation. The hydraulics, which includes uncertainty in the breach and the floodplains, all of that is input to the consequence model. The consequence model itself has other inputs that we'll discuss in more detail. Every consequence model out there has these few essential elements. It all has to start with an initial distribution of people within the floodplain. That's your population at risk. After that's set, there are protective actions to relocate those people out of the floodplain or even within the floodplain sometimes. So we need to understand the impact of warning and people's response to that warning and the timeliness of those responses. So how much time is available before the flood arrives, for example. So the other major piece then of that model is to understand the flood itself. How fast does that flood arrive before the warning happens or after the warning happens? And then what depths and velocities would people be subject to? That can be done in various levels of detail. The last thing is to understand the protection afforded by the final location. So where are people when the flood interacts with them, and how much protection does that location give them? Are they caught in a structure? Are they out, as a pedestrian in the flood by themselves, or are they in a vehicle possibly? Each of those situations has different results. And then we apply the fatality rate based on the situation that someone is found in, or, as I mentioned, for a more simplified model that could be applied to larger populations at risk. Here's a smattering of some of the tools that are available for consequence assessment. In the United States, dam safety best practices highlight two methods. The first is RSIM, which is a desktop methodology developed by the Bureau of Reclamation, and it's a little more simplified for easier, less complex scenarios with less consideration for evacuation in general. HEC-LifeSim is, as Krey mentioned, an agent-based software where it tracks the movement of every person through the progression of the flood and evacuation. There are other ones available too. HEC, the precursor to LifeSim was FIA, Flood Impact Analysis software, which is still available from HEC. And it has a more simplified evacuation routine in it. So it's kind of been replaced now in some part by LifeSim. Another agent-based model is the life safety model, developed by BC Hydro originally and now taken over by HR Wallingford. And in the Netherlands, a model called Evacuate, which is paired with an evacuation model, and then this applies fatality rates to the evacuated population. And there are a whole host of others that are a little bit older in generation and I have less familiarity with, but listed there in the lower right. Bas Jonkman in the Netherlands developed this chart to kind of understand model complexity as part of his PhD thesis, and this was done in 2007. You can see kind of the range of available consequence methodologies all the way from Decay and McClellan on the lower left, and the Graham method developed at Reclamation, Jonkman's own method there, IPET, which was done after Katrina in New Orleans. Utah State University model was developed by Dr. Bowles and was a precursor to LifeSim, also called LifeSim. And then you got BC Hydro life safety model and flume tests that were there. So on the left axis, the vertical axis, you have the level of detail. So is it tracking things on an event basis, a single event, or is it tracking them all the way down to the individual level? And then on the x-axis, you have whether it's empirical or mechanistic accounting for life loss. And so the mechanistic models are those that model the individual behavior and the causes of death for that, whereas the empirical models relate mortality to an exposed population to the event at the event scale. And so this was developed in 2007. There's been lots of advancement in modeling since then. And so I've added the models that I discussed earlier and kind of put them on there. So LifeSim is kind of somewhere in between empirical and mechanistic, but very micro level. There was a tsunami evacuation model developed at Tohoku University in Japan. That's much more mechanistic. And then you see the other ones there. So when you're selecting a model, it's important to consider the amount of investment you want to make in reducing uncertainty and what results you might be willing to accept. So things to consider. When does it matter to reduce the uncertainty? What's driving the uncertainty? Can we do something about it? And what decision are we trying to make with the results of the consequence analysis? So consider a consequence output down here in the lower left, represented by the blue box. We've got a dam, for example, that has 2 orders of probability in its annual probability of failure, and pretty much low consequences between 0 and 10. So is that something we'd want to invest in further understanding the consequences, or are we okay with just that answer? Contrary, you have a huge box up here in the upper right corner. You've got anywhere from 10 to 10,000 life loss roughly, and a really high annual probability of failure. Depending on the decision you want to make, is it worth the investment to shrink your box to the size shown here, or do you really have enough information to move out and try to mitigate that risk with the information you have? The last one is this. You got a really well-defined model, but it's kind of on the guideline, and maybe it's worth some extra investment to reduce that risk even further. Okay, the data requirements for a model. These agent-based models typically have a smattering of input parameters that are the same for any of the models pretty much. And the first is hydraulics. The second is a structure inventory. So that basically houses people in a location geographically to start the simulation. Then you need to populate those with census data and demographics. Then the next thing is a road network, so people can follow a path to evacuate. And then LifeSim in particular uses emergency management zones to distribute warnings through the populations. And then warning communication delays, there's a host of those different delays. I'll talk more in detail later. On the right is an example of what that input looks like in LifeSim. Some of the advantages of a consequence model. This agent-based model tracks evacuations and estimates fatalities on a one-to-one basis, every person in the floodplain. It incorporates two-dimensional unsteady hydraulics, so you have depth velocity and depth times velocity at every location where people may be. And you're using the actual road network to estimate evacuation as opposed to some simplification of it. That allows you to track the traffic in that evacuation network as well. One of the cool things about LifeSim is that it also includes a timeline of warning delays and how the warning spreads through a population through different channels like television, radio, or even Twitter or Facebook. So how that spreads. And then, there's a delay also for people to figure out what to do with that information and contact family members or move their valuable possessions to a safe place. Another cool thing that LifeSim does is it takes advantage of structure material and structure height information. So you know what a structure is made out of. This data is typically available through FEMA that has this database, or it could be available through real estate or government parcel data, that type of thing. And so you can actually calculate the stability of that structure in moving water with some other information. In addition, we can calculate the stability of cars and people at the point where they would contact the water. LifeSim also allows for Monte Carlo sampling, so we can look at uncertainty and a whole host of parameters and see the impact of that assumption on the life loss. And you can visualize results such as these plots, maps, and such to the right. Okay, so now how do we actually build a consequence model? The physical world is described with three main inputs. The first is the floodplain, typically in two-dimensional, but we can also pull in 1D and create maps with a 1D model. The second is a structure inventory. As I mentioned, it's the starting place for all the people. And third is the roads and the destinations at the end of those roads where people will be trying to reach. So what defines a structure in the structure inventory? There's a few examples here in different structures, multi-family housing, single-family housing, and commercial or industrial structures. So the first thing is the number of stories. How tall are each of those stories, the height, so we know if it is compared to the depth when people are impacted by the water. In addition to that is the foundation height. How high off the ground is that structure set? Do you have access to the roof or an attic? What kind of occupancy is it? As I mentioned, commercial, residential, multifamily. What is the use of that building? And what's it made out of, the type of construction? Is it reinforced concrete and steel, or is it, wood or timber framed? How many people are in the structure? what's the value of it if you're going to do an economic damage assessment, and the contents as well. Some of the sources of this information are government or real estate parcel data. You could also develop this information from aerial photos and public GIS data, such as Microsoft or Esri has some of this data available for free, or you could develop it manually by field surveys. Road networks are basically just, represent the connectivity between road segments, and they include bridges and one-way streets and divided highways. The most important part really is the capacity of the roads, defined by the number of lanes and the speed of the maximum speed of vehicles on the roadway. Destinations, represented here by the stars on this road network, are places where people will attempt to evacuate. And here we're trying to get everyone outside of the flood zone, but you could also place that destination inside the flood zone and to represent a shelter, maybe a building that's elevated out of the floodplain that would be a safe haven. Either way, the people are considered safe once they reach that destination. And the destination is selected in the model based on its proximity to the person's starting position. Okay, so LifeSim uses a timeline of warnings developed by some prominent social scientists, Dennis Milletti and John Sorensen. And this timeline described here starts with recognition of a hazard on the far left. This is a case for, let's say, a dam or a levee breach. So at some point, the hazard begins, meaning that the breach starts to take off, and you can see the hydrograph really rise steeply. But hopefully, it's recognized at some point before that. So there's a delay, or there's an amount of time between recognition of the hazard and the actual hazard occurrence, which really kicks off the whole timeline and the beginning of all the delays in getting that message to the public and the public doing something with that information. So you've got a delay from whoever discovers the hazard to the person making a public warning declaration. You have the delay for that agency to decide who to warn and how to warn them and what they're going to tell those people. Then you have a delay as that warning message spreads through the population. After that, people receive the message and they have a delay in deciding what to do with it. So are they going to contact more people or protect their property or leave immediately? And then once people decide to leave their starting place, there's a delay as they proceed through the floodplain during the evacuation until they reach their destination. All of these are considered within HEC-LifeSim. And each of those has uncertainty about it. That's represented by curves such as these for the warning issuance delay. Depending on how well prepared the emergency management agency is, you may have a shorter or longer delay in this warning issuance. Drs. Milletti and Sorensen also gave some really important content on the most important thing you can do as an emergency manager to motivate the public, which is create an effective message. So that message should have information about the source, who's saying it, where the threat is coming from, the location of the threat, and where people should go for safety, direct guidance to them and how soon they should accomplish it, and then when the message expires. This is all documented in a report that they did for the Army Corps of Engineers called A Guide to Public Alerts and Warning for Dam and Levee Emergencies. When people leave their structures, there's several protective actions that they could decide to take. First and foremost is evacuation, whether on foot or in a vehicle. They may also decide to vertically evacuate to upper floors in a building or onto the roof, for example. Some people may leave the structure to go to another structure, which we would call sheltering in a stronger or taller structure. Some people may be caught unaware and not decide to evacuate until the flood has actually arrived, in which case I use the term fleeing for that, meaning that they're evacuating through the water. And there are certain cases where that may be modeled. And the last is rescue, which is difficult to include in the consequence modeling software, but it is a consideration if you have helicopters or boats or things like that are really contributing to reducing the population at risk. This is an example here of how that warning propagates through the population. The structures turn yellow as they receive the warning. After a delay, they decide to evacuate and they get in their vehicles and follow the roads to the nearest destination. Another interesting aspect in a demonstration here from a levee breach in Japan. So every structure has a material type associated with it, and there is a stability threshold associated with that material. So for, let's say, wood framed structures like these in Japan, there may be a maximum and minimum stability threshold based on depth of and velocity of flooding, and some uncertainty between there where the structure may or may not collapse. You can see here, a lot of these structures did collapse during this levee breach, and we were able to calculate those in LifeSim. Now, there are lots of examples of these hazard criteria curves that have been done for different reasons. This is one of the best at the University of New South Wales, really on the cutting edge of research. They pulled together other studies on the stability and submergence limits for people as they're walking, vehicles as they're driving through floods, and buildings, different types of buildings. So that's a great source of information. And then the last piece of the consequence model is application of the fatality rate. So here's a couple examples, the lower left from that Bos-Jonkman's dissertation, on the right from HEC-LifeSim. Both of these and others are based on historic documented cases of fatalities, and it's applied typically to a group or in the case of LifeSim down to the individual level or the evacuating group. But it could be applied on the scale of the entire population at risk as well. And these fatality rates are typically divided or separated by hazard severity. So for LifeSim, you've got low and high hazard zones. For Jonkman's method, you've got the zone of rapid rise, or the breach zone, which you're very close to the breach. And then you've got the more slow rise zone further away from a levee breach. As I mentioned, there's a Monte Carlo simulator in LifeSim, so you can account for uncertainty. Here's some of the parameters that have that uncertainty and kind of the distribution of results that you can see. And as I mentioned before, really the final step in your consequence modeling, while you're presenting the results, is to not dwell on a single answer, but really to build the case for why the results are the way they are. Why was it modeled that way? How it was modeled? What are the sensitivities and the uncertainties in the results? And why does it make sense or not? So really, it's providing the context to those results. Here's a couple examples of other visualizations that are in LifeSim, and other models have similar ones. You can animate things or map them in 2 dimensions. On the right, there's a heat map of life loss, and so you can see where life loss is occurring most. And on the lower left, you see vehicles exiting every destination point. You can see how people are accessing that location over time, so you can have a good understanding of bottlenecks and the efficiency of evacuation routes. There's also many tables that I'm not showing here, but lots of information available as model output. Another example of an evacuation simulation as an output. This one you can see where the hydraulics are interacting with vehicles and structures, and trapping those people at that location, and in which case the high fatality rate would be subjected. So what do we do with the model output? It's really a great tool to better understand risk, right? Both in damages and life risk. You can also understand major uncertainties and sensitivities in the data and recognize evacuation bottlenecks. It's important to be able to understand risk drivers in your overall risk assessment if you can quantify the difference between a gate failure versus a dam failure, for example. And then you can look at the impact of risk reduction measures. Some considerations are obviously the time and cost to invest in one of these models. It's not the solution for every problem. So you can make fast LifeSim models, or you can make very detailed LifeSim models. But it's also a consideration of your data availability. So if it's not publicly available, you could consider purchasing some GIS data, for example, or doing field or manual collections. Where can we use LifeSim? I'm sure you guys have lots of options out there and things you've thought about that I have not considered, but here's a few that I'm thinking of. Where I've used it in the past is flood risk assessments for dam and levee safety, making decisions about infrastructure investment, so mitigating risk, in both structural investment, but also non-structural. So you could consider the impact of public education and outreach, for example. And that becomes really important for emergency management planning. And then, we're starting to think about other disaster evacuations. As far as I know, it's never been applied to a tsunami, but there's a capability to input any two-dimensional grid into the model, so it could easily be done. And I'm also working on a project to try and adapt this to wildfire or bushfire simulation. So instead of a floodplain, we add a raster series of wildfire propagation and evacuate the same way. So lots of options out there, and I'm sure you guys have more. With that, that's the end of my presentation, and I'll turn it back over to Krey to talk through some of the questions in Q&A. Thank you.
Okay, well, thank you for that, Paul. I'm going to share my screen here and walk you through a couple of things that are specific to Australia and that have worldwide application as well. What I'm going to do here is just step you through a couple of things that have been done, and this did come up on the chat line, so those Australians on the line can be proud of the fact that we are on the cutting edge here of some of this research. You may be aware of University of New South Wales, some of the studies they've done. If you watch what happens there as they're pushing these things around, it's amazing how little force can actually move a vehicle once it's buoyant. There's a research paper here I'll put in a link to this one's based out of Stuttgart, of all places, where you'd be wanting to have a surplus of cars available to test here. I'll put a link to this again in the chat line or in the Q&A line if you're interested in downloading some of these studies. Now, we did put a link to some of these visualizations in the webinar registration page. You might want to have a look at those. The Weather Channel has done a few of these that I thought were pretty cool. Even though they do it in English units there, the 3 feet. Have a look here at the DV plot if we're going to talk about hazards to people or individuals, vehicles, and buildings based on the depth times velocity. If this water's not flowing, look at this velocity being nearly zero. As you get the depth increasing, it becomes a little more dangerous as you get to these deeper depths, like above 12 feet or 4 meters. And so just visualizing that can be helpful, especially when you look at, boy, that's a scary scenario there, when you look at what's going on inside the vehicle. I think that's something that we've all, had maybe some nightmares about in the past. But when you watched what he did with one finger pushing that vehicle away, it does show you how buoyant a vehicle becomes. Now, one thing to be aware of as well is newer vehicles they've found in the latest research are much more susceptible to floating away because they're more airtight and they're also probably a bit lighter than the older vehicles. In Australia, again, I'll highlight these links in the Q&A line. We've got a flood risk information portal where you can actually go online and either look up flood studies that have been done or upload your own. And it's not just flood studies, but any data that, that Paul has discussed that would be useful in doing a consequence assessment can be extracted from this database or uploaded to the database when you register. I want to do a little bit of a highlight then, take about 2 minutes to introduce a topic we'll be covering in a few months' time that does relate to this. And that is when we look at these depth times velocity plots, this is included in Australian rainfall and runoff guidelines as well. I want to make sure we can all understand or come away from this with an understanding of what D times V actually means. And so when we get these ISO lines, like you see here, a velocity of 2 meters a second, which is fairly typical for a regular river just flowing normally, at a depth of 2 meters is on the threshold of being unsafe for structures, vehicles, and individuals. That's your 2 times 2, which is your 4 meters squared per second ISO line. Take that down to 1 times 1 down here, and it's a bit less. And you can see where it has a different classification. Now, one thing I wanted to highlight, again, for an upcoming webinar we've got in trying to protect riverbanks and things from the damages resulting from flood waves, is the depth times velocity plot. And this is actually a question that Marty Jacobs, looks like, on the chat line has asked. He says in the chat line, most hazard assessments refer to the DV product as the prime indicator. I suggest this is a historical artifact, and a better parameter would be shear stress, also a function of D times V, which is implicit in the hydraulic calculations and might provide better linearity. And this is something, again, if you can tune in on our webinar coming up in about 2 months' time on shear and riprap protection. If you look here, the same velocity, a 1 meter a second velocity, in this case and in this case below, can have a different effect on people, vehicles, and structures. But in order to get the same velocity out of these two scenarios, you need to steepen up the slope in order to get this depth times velocity product. Down here would be 1, and this would be a depth times velocity of 2. Now I'll ask you a couple, one teasing question here to lead up to that next webinar. When we look at these equations, what's really odd about these is it's inversely proportional to the depth. So that when we look at these charts on what it could move, could this flood wave move a building, a person, a structure, we think about the strength of these things. And when you look at these water depths, for example, a 20-meter water depth, that's really, really deep, would probably be standing still. I don't think you'd ever have a 20-meter wall of water moving unless it's a dam breach. But in that case, yes, it will pull some structures off their foundations. And I'll highlight the zone of applicability here for these equations that were used to derive these curves here, and also plot on here the riprap classes. And this is in response to Marty's question, I guess, using a velocity-based versus a shear-based approach can have drastically different results as far as the recommended size of a boulder that would stay in place in the case of a flood wave arrival. Now, again, think about this in terms of people, buildings, and vehicles, and what it would take to move it. Here is a 20-meter depth plotted at 5 meters per second. So that's an ISO line of 100. That was way off the charts. Here's one of 5 times 5, which is 25. And then here's one of 2 times 5, which is 10 meters squared per second, which is kind of getting onto the chart, but still dangerous. All of these could move things. Now, the question I'll ask you, and this is for the nerds in the audience, those engineers out there who use these equations, whether it's velocity-based or shear-based, to tell you what's going to stay put, what will not move under incipient motion conditions, have a look at whether you think this is counterintuitive. A 100 dV squared versus a 10 dV squared. This is 10 times as high down here. But think about the direction we're going. Look at the size of riprap you would need. Why would you need larger riprap for the shallower depth? Okay, And that's a leading question, because we're going to cover that topic in detail for the nerds in a couple months' time when we do a webinar on riprap bank protection and stability and incipient motion, and how you should be sizing things these days based on shear and or deep V, or on velocity, or any other energy method. So it's a hot topic for everybody who's in flood management. Now, with that, I'm going to stop sharing my screen, and hopefully we can get Woody and potentially Mark and Paul to come back on board. And let's have a look at some of the questions that have been answered, and let's open this up for discussion. So maybe start with Woody. I see that you've answered a couple of questions here already. Any of those you'd like to highlight, because those watching the recording won't actually be able to see these questions. So it'd be good to see if you could highlight some.
Sure, absolutely. So one of the questions was, let's see, can you model, can the model evaluate only economic losses? For example, for a location that is exposed to floods, but fortunately hasn't had life losses before. So if you're only interested in economic damages, yes, it can be set up to evaluate economic losses only. And one of the good things about that is that you don't need nearly as much data, right? So if you're only modeling direct economic damages, you don't need a road network. You really don't need to know about the evacuation timeline, so it can really help out in that process. So you can use summary grids like a maximum depth information as opposed to the time series of depths and velocities. Another question, does LifeSim account for demographics of population at risk, such as average age or income, which could play a factor in ability to evacuate via vehicle? And I answered that yes, to some extent. So LifeSim does have the ability to set a certain percentage of the population that will evacuate on foot. And you can build into the evacuation relationships, for example, how quickly people mobilize by based off of the demographics of your area. So if you have an area that's generally going to be kind of a tight-knit community who doesn't trust government messages, doesn't necessarily trust a warning message that's coming from whatever police forces in the area, then you can build that into the curve that their actions will be much slower to actually take those protective actions to evacuate. So you can build that in. Now, it doesn't account directly, though, for people that need to use public transportation. So buses and trains, those aren't built into the model. So that's going to take a little bit more effort.
Sounds good. One question just came up. Has the model been validated using recorded flood events and fatalities?
That is a good question, and one that we've been actually, it's very topical. We have validated LifeSim against various flood events in the past. Hurricane Katrina, the New Orleans East Bowl, we've validated against that. We validated against the Joso levee breach event, Malpasset dam failure, Kelly Barnes dam failure, and we're starting on the process of finding more. It's really hard to validate a life loss model because it's really hard to get the data to support that validation, especially for agent-based. And so we've really been taking a lot of effort ourselves and others in trying to collect enough data for these events to be able to validate. And so far, our validation efforts have been fairly fruitful. Some of them have shown us where the model may be missing a little bit, but we can explain why, and that's very important.
Yeah, thanks. Question over to Mark about 1D versus 2D when you're using your flood results. Using the inputs from your flood model outputs. Just wanted to see if you wanted to comment briefly on the applicability of using a 1D model for some of these scenarios, just in the interest of saving computational time.
Well, obviously, the one-dimensional model is going to have a much more simplified version of what actually takes place, and the flow into the overbank is oftentimes a lot more complex than a 1D model is going to capture. And when you're dealing with these kinds of responses from the public to evacuate, you need to get that information in the overbank accurate. So as that flood wave propagates into the overbank, you want an accurate solution. 1D model in many instances is going to give you a very coarse answer, and therefore your results are going to be influenced by that coarse answer.
Yeah, and I think inherently, when you look at the maps that Paul has put up, those models that you see in those simulations, at least, the flow is not one-dimensional in nature, and you'd have a real tough time trying to define individual flow paths and lay out your cross sections in a way that they always stay perpendicular to the flow direction and with a flat water surface across the top, which is the underlying assumption there in the 1D models. Any other questions then you wanted to highlight there, Paul or Woody, if you guys have a look just at even at the ones that have been answered?
I thought there was a couple of questions there that I thought Woody or Paul could answer with regard to the inputs what model sources can be used as input, and how do you improve the accuracy of the simulation. I thought those were good questions.
Paul, you want to tackle one of those?
Sure, I'll tackle the first part and then probably hand it off to Woody. As far as what hydraulic data can be used in LifeSim, the preferred option is obviously HEC-RAS, because the two are linked fairly closely, both developed by the Army Corps. But it has the option to pull in ADH, which is developed by the research lab at the Corps, Flow2D, which is probably more popular in the US, and then really any two-dimensional rasterized output can be used if you can develop a time series of depth and velocity grids. That's kind of the most simplified way to import it. And then if you, like Woody said, if you don't want to do the evacuation modeling, you can just have summary grids which talk about maximum depth and maximum velocity. And Woody, maybe you can take it a little further than that.
Yeah. So it's really designed to be able to take in that being able to take the time series of grids makes it so that pretty much any hydraulic model output can be used in LifeSim. It just has to be converted first, and that's really the key.
Sounds good. And if with our Australian audience, of course, I use mostly TwoFlow here in Australia, and we actually do have a webinar coming up on some of the new innovative things that have been getting entered into TwoFlow, as well as into HEC-RAS. We'll have a couple of these webinars coming up, so do tune in for those. And yeah, we in a presentation like this, we like to show you what the inputs and outputs are, what the things are to be concerned. Which model you choose to run with, may depend on which circumstances you might have for your individual project area. But the key is knowing the reliability of the data that you're feeding into it. The old garbage in, garbage out scenario. If you know what the model is sensitive to and you know what you need to collect, you can make your choice of model at that point. But no model is going to give you good results with bad input data. So with that, Paul, Mark, Woody, thanks for coming on board. I'll have you guys each just do kind of a final summary, little comment, closing comment before we exit.
All right, thanks very much. Thanks, Paul, for that presentation. If anyone has any questions on LifeSim, I'm always open for any information. So you can, if you find any good research you think would be useful, send them my way. If you have questions about the software, also send them my way.
Sounds good. Over to you, Paul.
Thanks, Krey. I appreciate the opportunity to present on what I think is a pretty cool piece of software I like to geek out about. So yeah. Hit me up if you got projects that you want to use LifeSim for. Thank you.
Sounds good. Mark, closing remarks?
Not a whole lot to offer. And Paul and Woody did a great job of presenting a very complex tool, and it shows how our industry is very rapidly developing to answer the questions that we have to solve as hydraulic engineers and floodplain managers to manage the risk that the public is exposed to from these types of this kind of technology development so rapidly.
Sounds good. The last question, it says, when will HEC-RAS 6 or 5.1 be released? We're not even going to answer that one. So we'll leave that one for another time. Stay tuned for upcoming webinars on the. So thanks for a couple comments just coming in. We'll try and get to you individually on that. Time is up now. So thanks so much for tuning in. Have a great day, guys. Thanks for your participation.